Lesson 5-7 Measures of Variation, and in this lesson you learn to calculate and interpret range, quartiles, and interquartile range of sets of data. Why is it important? Because measures of variation can help you easily describe the spread of a set of data. So let's take a look at this example on climate. Justin Williams has been promoted and has the option of relocating either to Columbus, Ohio, or San Francisco, California. The Williams family lives in Tampa, Florida, where it is usually warm all year long. His family's wardrobe includes basically all lightweight apparel. He wondered if moving would mean they would have to get lots of new clothes. He looked at the average high temperature for the two cities and found the following information in the table of average high temperatures of US cities. Okay? And this is what he found on this chart: Columbus and San Francisco, the average temperatures in January, February, all the way to December. So Mr. Williams calculated the mean and the median of the temperatures of each city. The mean high temperature for Columbus, Ohio was 63.5, and for San Francisco it was 62.4. So the median high temperatures for Columbus was 63.5, and for San Francisco it was 63. So they're almost the same, very close to each other. So he figured that that meant that the climate in the two cities was just about the same. But then he decided to take another look at the temperatures and find another way to analyze them. So Mr. Williams actually looked at uh, the mean, median, okay, and there was no mode, so he looked at those methods of finding out the average temperatures, okay, for Columbus and Ohio, and he found uh, that they were almost the same. But he wanted to find out more, so he looked for another method. Okay, so the months and temperatures, okay, for each city form what we call a relation. You know what the relation is from the last lesson. Mr. Williams decided to graph the relation for each city. The month at the bottom, remember we always graph the time on the x-axis because it is always the independent variable, and the temperature is on the y-axis. The months and temperatures for each city form a relation. Mr. Williams decided to graph the relation for each city. He used different colors for each city. Okay, green is for San Francisco, purple is for Columbus. And if you notice, San Francisco has a flatter graph compared to Columbus, Ohio. Okay, so what does that mean? Let's find out what it means. Okay, he noticed a pattern. Okay, in the temperatures was very different. This case shows that measures of central tendency, which is what he did first, finding the mean and finding the median. Okay, the measures of central tendency may not give an accurate enough description of the data. Often measures of variation are also used to describe the distribution of data. So he wanted to use another method aside from the measures of central tendency. He wanted to use measures of variation, another way to analyze the distribution of data. Okay, so one of the most common measure of variation is what we call the range. Unlike the other definition of range in this chapter, the range of a set of data is a measure of the spread of data. So let's define range. The range of a set of data is the difference between the greatest and the least values of the set. And if we want to find the range, okay, for each set of temperatures, okay, we have to make a table to help us organize the data. So in Columbus, the greatest temperature in Columbus was 84 degrees, and the least temperature in Columbus was 35 degrees. So the range would be 84 minus 35, or 49 degrees. In San Francisco, the greatest temperature was 69 degrees, the least temperature was 56 degrees. So the range, or the spread of data for San Francisco, is 13 degrees Celsius. Okay, so the range of temperatures for Columbus is greater than that of San Francisco, 49 to 13 degrees. This means that temperatures in Columbus vary more than the temperatures in San Francisco. Okay, so if you have a large range, in this case you have a large data spread. In Columbus, it's 49 degrees. In San Francisco, it's 13 degrees. This simply means that it will vary more, okay, for the data with a larger spread. So if your data has a greater range, that means it will vary more than the data with a lot less range. Okay. So if his family moves to Columbus, he will definitely need some new clothes for colder winters. Okay. So let's talk about another method. Another commonly used measure of variation is called the interquartile range. So in a set of data, okay, in a set of data, the quartiles are values, okay, that divide the data into four equal parts. Okay, so statisticians often use Q1, Q2, and Q3 to represent the three quartiles. Okay, remember that the median separates the data into two equal parts. We learned this previously. Q2 is considered to be the median of the set of data. Q1 is our lower quartile, and it divides the lower half of the data, okay, into two equal parts. Likewise, Q3 is the upper quartile, and it divides the data, the upper half of the data into two equal parts. So, when we studied measures of variation in the past, okay, we did not assign Q1, Q2, Q3 for them. Now we are assigning them. When we have Q1, that means that is the lower quartile. Q3 will be your upper quartile, and Q2 would be your median. Okay? So the difference between the upper and lower quartiles is what we call the interquartile range. Okay? Or the IQR. So let's define what IQR is. IQR, the interquartile range, is the difference between the upper quartile and the lower quartile of a set of data, and it's called the interquartile range. It represents the middle half, or 50% of the data in the set. Okay, so the interquartile range basically, okay, represents the middle half, okay, or 50% of the data in the set. Okay, now we got that down. Okay, let's move on to our examples. Let's take a look at example number 1. The table below shows the heights and weights of 13 players on the 1999 Dallas Cowboys football team. Find the median, upper, and lower quartiles and the interquartile range for the weights of the players. Okay, so first that we need to do here are the players: Aikman, Harper, Hellstray, Irvin, Johnston, Lester, and so on and so forth, all the way down to Woodson. Okay, and these are the weights in pounds: 220, 219. The first thing we need to do is we need to order, okay, the 13 weights from least to greatest, and then find the median. The least weight is 198, and the greatest weight is 311. And if you count the number of the pieces of data, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that means that the seventh piece of data will be the median, because that's the middle of 13. So 1, 2, 3, 4, 5, 6, 7. So 220 will be our median. Okay? So to be able to find the lower quartile, okay, the lower quartile is the median of the lower half of the data, and this is the lower half of the data right here. Okay, from that point to that point is the lower half of the data, and the upper quartile is the median of the upper half, and this is our upper half. Okay, if the median is an item in the set of data, it is not included in either half. Okay, so let's find our lower quartile and upper quartile. Okay, In this case, our Q1 and our Q3, because our median is our Q2. So this is Q2 right here. Okay, so in order to find Q1, we get the lower half, which is 1, 2, 3, 4, 5, 6. And if you notice, it says here, if the median is an item in the set of data, it is not included in either half. That means if 220 is one of the data that we have, then we will not include 220 in the lower half. So in this case, we do not include 220, and we only have 198 to 219. And if you notice here, okay, there are 6 pieces of data. That means to be able to find the median of the lower half, okay, we get 207 plus 209, divide that by 2, which will give us our Q1, or our lower quartile, which is 100 or 208. Okay, on the other side, to find our Q3, or upper quartile, we simply add 242 plus 290, divide that by 2, we'll get our Q3, or our upper quartile, while maintaining 220 as our median. Okay, so the interquartile range is 266 minus 208, or 58. Therefore, the middle half, or 50% of the weights of the football players varies within 58 pounds. Remember what we talked about in IQR? Okay, IQR, or interquartile range, is equal to your Q3 minus your Q1. Okay, and this is your upper quartile minus your lower quartile. So the variation, okay, the weights of the players varies 58 pounds, because that is our interquartile range. Remember that the median is the middle number when the data are arranged in numerical order. That's just a reminder for you to be able to find the median. Okay, so moving on, in example number 1, which we have, suppose that the greatest weight was 355 pounds instead of 311. So let's say instead of 311, that weight becomes 355 pounds. Okay, in a set of data, a value that is much greater or much less than the rest of the data is called an outlier. Okay, and we define an outlier to be any element of the set of data that is 1.5 the interquartile ranges greater than the upper quartile. So again, an outlier is defined as any element of the set of data that is at least 1.5 interquartile ranges greater than the upper quartile or less than the lower quartile. What that means, if we want to put that, okay, in symbols, is that your outlier, the limits of your outlier, okay, the limits of the outlier would be equal to your the upper limit for this instance. So your upper limit, which is our UL, will be equal to 1.5 your IQR, 1.5 times your IQR, and add it to your Q3, or your upper quartile. The lower limit of your outlier will be your Q1 minus 1.5 your IQR. Okay, so that means beyond these two limits, it is considered to be the outlier. So if it's beyond the upper limit, then it's considered to be an outlier. If it's below the lower limit, it is also considered to be an outlier. Okay, so what does this mean? If you look at our data, okay, one more thing before we go to the next one. An outlier will not affect the quartiles, but it will affect the mean. Okay, which simply means it will affect the average of your set of data in terms of measures of central tendency, and it will affect the mean of that data. Okay, and the interquartile range of the football data, like going back here, is 58. So we multiply 58 by 1.5, and that will give us 87. And if you look at our data here, the one that we have on top, we know that 220 is still our median, our Q2. Okay, and we get 87. First, we find our lower quartile and upper quartile. We know that this is our Q1, our lower quartile, and Q3 is our upper quartile. And from what we know, to be able to find the upper limit of our outlier, we need to add 1.5 the IQR, in this case 87, to upper quartile, and that becomes our upper limit. So 353 becomes our upper limit. And if we want to find our lower limit, Q1 minus 1.5 IQR, or Q1 minus 87, so we subtract 87, this becomes our lower limit, which means that anything beyond 353 is an outlier. Anything beyond 121 is an outlier as well. So if you look at our graph, we have one piece of data that is beyond 353. That means, okay, there is an outlier. 355 is considered to be an outlier, and this is the only outlier because that is the only piece of data that is beyond our upper and lower limits. Okay, and those are what we call outliers. Let's take a look at the last example. The double stem and leaf plot below represents the tonnage of domestic and foreign imports being delivered at the top 19 busiest ports in the United States during this recent year. Okay, so you have your double stem and leaf plot, and if you look at your double stem and leaf plot, you have brackets, a blue square, a triangle, another blue square, and another set of brackets. Okay, so let's see what these mean. The brackets group the values in the lower half and the values in the upper half. So you have your brackets, okay, here. So this is our upper, okay, half of data, okay, and the other bracket is our lower half of data. What do the boxes contain? What do you think the boxes contain? So the boxes contain our upper quartile and obviously our lower quartile. Okay. And letter B, find the interquartile ranges of the domestic and foreign tonnage. And letter C, which type of imports had more consistent tonnage, domestic or foreign? Okay, let's answer letter A again. Okay, the quartiles contain, okay, or in this case, the triangle contains, the two triangles in this case will contain, okay, the median. Okay. What do the boxes contain? The boxes will contain our quartiles, upper and lower quartiles. Okay. And in letter B, find the interquartile ranges of domestic and foreign tonnage. And from what we know already the upper quartile in this case, it's our upper quartile is 40. Okay. Okay, 40,000 tons, and our lower quartile is 40,000 tons right here, and our lower quartile will be 15,000 tons. So to be able to find the IQR of the domestic, okay, we have Q3 minus Q1, or 40,000, 40 minus 15, which will give us 25. Okay, so Q1 is still 15 and Q3 is 40 according to the blue boxes. In our foreign, okay, foreign data, you have 36 and 20. Okay, 20 is our Q1, 36 is our Q3. Our QR therefore would be Q3 minus Q1, or simply 16. 36 minus 20. Letter C, the foreign imports. Okay, the foreign imports had more consistent tonnage because it had a smaller interquartile range. So when you talk about foreign, the interquartile range, it is more consistent when the interquartile range becomes smaller. And if you look at the domestic imports, it's 25, which is a lot greater than 16. Okay, and finally letter D, let's find our outliers. Okay, outliers are those values that lie 1.5 IQRs above the Q3 or below the Q1. And if we write Okay, the limits of our outlier, upper limit would be equal to your upper quartile, or your Q3 plus 1.5 IQR, and our lower limit would be our Q1 minus 1.5 our IQR. Okay, let's just put that in parentheses right there. Okay, so let's find out. Anything beyond these two limits will be an outlier. So for the domestic, okay, 1.5 the IQR plus Q3 is, since our IQR is 25, we get 1.5 of that plus 40. So our upper limit would be 77.5. Okay, and our lower limit would be Q1 minus 1.5 IQR, which is 15, minus 1.5 IQR, which is negative 22.5. So if you look at our set of data, okay, since 105 is greater than 77.5, 105 is an outlier. Okay, and there are no outliers below negative 22.5. And this is where 105 comes in, right here. See, 105 is beyond our upper limit, and therefore it is an outlier. For the foreign imports, let's do the same thing. Okay, 1.5 IQR plus Q3. So our upper limit for foreign imports would be 60, and our lower limit would be negative 4 using the same formula. And if you look at our data, since 95 is greater than 60 and 73 is greater than 60, we have two outliers for our foreign imports, 95 and 73. And there are no outliers below negative 4. Okay? And that's it for this lesson. Thank you for watching.